Howdy, everyone. Good morning. How are you all doing? I'm doing good also. Doing good. Finally got vaccinated, which is nice. And I didn't feel like crap the next day, which is also nice. So okay, why is it like this? Hang on. That's better. Okay. That's what was happening there. Guess it was all smudgy. All right, that looks better. So yeah, doing good. Alrighty. So first of all, is everyone able to see the homework, the written homework under assignments? Okay, I will do an upload thingy. Oh, hang on. Okay, yeah, I will do an upload thingy for that. And also going to figure out, in fact, I think I might, I'm not going to say anything. I will send it out an email. I need to talk to the course coordinator about something, but yeah, I'll send out an email later today with more info on the quiz. It's either going to be on Wednesday or Thursday. I would like it to be on Thursday. I think that would make more sense, but I'll send out an email today. Yeah, it definitely would be when I figure that out. Yes. Okay. But yeah, the quiz is going to cover the same material as the homework, the same sections, same sorts of things. And it'll be a short 3-question quiz. And you will do the same thing, write down your work, scan it, and upload it to Canvas. Yes, yes, I will do that. Yeah, I can do that. Yes, that would be good. Okay, any other questions about that? Okay, cool. So let's finish up looking at conservative vector fields and the, they don't refer to it as such in this book, but it's called the fundamental theorem of line integrals. And it is very nice. Okay. Alrighty. So remember, conservative what a conservative vector field is, is it's a vector field which is the gradient of some scalar function called a potential function. So f is a conservative vector field if there's some scalar function where if you take the gradient, you get this vector field. Whoops. So if it's equal to the gradient of some scalar function. And that scalar function is called a potential function. And I want to emphasize it is a potential function, not the potential function, because you can always add a constant to it. And when you take the gradient, you get the same vector field, right? So there are infinitely many of these potential functions, but they only differ by a constant. So we're conservative if we're the gradient of some potential function. And these have very nice properties, as we saw. So this is I'll write it down, the fundamental theorem of line integrals. And I will often just refer to this as FTLI. Says the following. This is why these are really nice. So basically, so if your vector field is conservative, if you're the gradient of little f, if little f is your potential, so if it's conservative, on some domain D, then the following things are true. So if C is any curve from a point P to a point Q, then the integral over the curve C of our vector field is just the potential function at Q, the endpoint, minus the potential function at the starting point, P. And that's true of any curve from P to Q. So all that matters are the starting point and the ending point. This is really nice. You don't have to parameterize your curve. You don't have to do this substitution and actually do the line integral. You don't have to do dr as r prime t, all that stuff. All you have to do is find the potential function if you know your vector field is conservative, and evaluate that potential function at the endpoints. That's all you got to do. So it works just like an antiderivative in 140 and 141. You just evaluate the antiderivative at the endpoint minus antiderivative at the starting point. That's all you got to do. It's very nice. Don't have to do an actual line integral. So I want to emphasize, this says for line integrals of conservative vector fields, path doesn't matter. How you get from point P to point Q doesn't matter. All that matters are the endpoints. If you change the path and you have the same endpoints, you still have the same integral, the same value. And that this is only true of conservative vector fields. Okay, so 2, so this is, you could derive this from the first bit. If you look at a closed curve, that's going to start and end at the same point. You can just pick any point on there and say it starts here and ends at the same spot. And so applying 1, you get the antiderivative at the starting point minus the antiderivative at the ending point, but they're the same. So you should get 0. So if C is any closed curve, then the integral around C, and I'll put this little circle there just to show that we're going around, integrating around a closed curve. You don't have to put that circle there, but that is a bit of notation that you see often just to emphasize that you're integrating around a closed curve. But the integral around any closed curve is 0 if you're integrating a conservative vector field. So in other words, if f is conservative, if you want to evaluate the line integral of f over some curve, you find a potential function, an antiderivative, and you evaluate the endpoints. It doesn't matter how you get from one endpoint to the other. All that matters are the endpoints. And if f is conservative, the integral around any closed curve is going to be 0. Yes, correct. So it doesn't matter which point you pick on the closed curve, but you can say my curve starts here and ends here. And because of 1, that's why it's 0. So by endpoints, I mean, so, right, so say here's P and here's Q. So suppose we're integrating along some curve in R2 or R3, depending on the setting. But the endpoints of the curve are just where you start. So if you imagine you're a particle moving along the curve, it's where do you start at time A and where do you end at time B? Does that make sense? So for a line integral, you don't get upper and lower bounds until you parameterize. And those upper and lower bounds are time A and time B. So the nice thing about conservative vector fields is you don't have to parameterize. You don't have to do that step where you replace x, y, and z with parameterizations, replace dr with r prime t dt, et cetera. You can just find an antiderivative and evaluate at the endpoints. And by endpoints, I mean the endpoints of the curve, the starting point and the ending point. Does that make sense? Okay, I'm going to assume it makes sense unless you say otherwise, because I got to move on. Okay. So basically, well, let me just write down another theorem. We'll see in a sec the process for, in general, evaluating line integrals of vector fields. And the first step is going to be, we're going to check to see if our vector field is conservative, because if it is, then we have a lot less work to do. We don't have to do an actual line integral. We just find the potential function and evaluate at the endpoints. So how do we check that a vector field is conservative, first of all? Well, this tells us how we do that. So if we have a vector field, F, and it's conservative, oh, sorry, no, nope, not yet. So it is just a vector field defined on a simply connected. I wouldn't worry too much about this. We're not going to try to get tricky on you. But this can fail if we're not simply connected. And if we have time, we'll look at an example of how that works. And so simply connected, I don't want to spend too much time dwelling on what this means, but we mean the domain is simply connected. So basically it means the domain consists of one piece. These are very not technical terms, but it means it's not like this is our domain D and it consists of like these two pieces here. It's going to consist of a single connected piece. So it's connected. If you take any 2 points in your domain, you can draw a curve from one point to the other entirely in the domain. You can't do that there. You got to leave the domain if you go from a point in one piece to a point in the other piece. So it consists of one piece, essentially. And this is also very not technical, but any loop, any closed curve, you can tighten that loop to a point. While staying in D. This is kind of difficult to describe, so I'll show an example. While staying in D. I'll show you how you can fail to be simply connected in a second. But I would say for the moment, don't worry about it. Everything you're going to deal with is going to be nice. We're not going to trick you on an exam with this. But so if you're a vector field on a simply connected domain D, then here's how we check that we are conservative. So here's the important bit. So your conservative vector field if and only if so if you're a vector field on R3, if the curl of F is 0, the 0 vector, that's how we're going to check that a vector field on R3 is conservative, is we're going to show that the curl is 0. And on R2, we're going to have the cross partials thing. So the partial of F2 with respect to X is equal to the partial of F1 with respect to Y. So if you take the second component and you take the derivative with respect to X, it's equal to the first component where you take the derivative with respect to Y. So these are the checks. If it satisfies these and you're on a simply connected domain, then you're a conservative vector field. So that's the kicker here. If you want to know if a vector field is conservative, then if you're on R3, you check that the curl is 0. If you're on R2, that's supposed to be a little bracket there, you check the cross partials condition. Okay, so that tells us if we just look at a vector field, how do we know it's conservative? How do we know that there is some potential function? Okay, so here's how we use that fundamental theorem. So if you're just given a line integral of a vector field, if we want to evaluate this in an exam setting or whatever, first thing you always want to check is f conservative? If so, we can save ourselves a lot of work. By not actually evaluating the line integral, but by using the fundamental theorem, finding a potential function in antiderivative and just evaluating at the endpoints. And we just saw the way we check that it's conservative is the curl 0 if we're on R3, is the cross partials condition satisfied if we're on R2. So if you check your vector field, you see that it's not conservative. You just have to go ahead and evaluate it as a line integral. Parameterize, plug in the parameterization, dr becomes r prime ddt, etc. Nothing you can do if it's not conservative. But if it is, conservative, then we need to find a potential function. Little f. And that's what we're going to talk about in just a sec. So we need to find the potential function, and we need to figure out the endpoints of the curve C, the endpoints P and Q. Where do we start? Where do we end? We start at P, we end at Q. So we find a potential function, we find the endpoints, and then from our theorem, the integral is just the potential at the final point Q minus the potential at the starting point P. In general, going to be a quicker process than doing a line integral. Okay. All right, so it's this bit, finding the potential function, that we need to learn how to do. So let's look at how we do that. Okay, but any questions so far? So we learned how to do, to integrate directly a vector field over a curve C, right? Parameterize, plug in the parameterizations, dr becomes r prime t dt, take the dot product, integrate from a to b, etc. It's a whole process. And but if our vector field is conservative, then we just need to find an antiderivative f potential function and evaluate the endpoints. Quicker, easier, less work involved. Okay. Okay, so here's how we find the potential. So suppose we've checked already that our vector field is conservative. I'll do it for R3, but the process is the same for R2. Finding the potential function. Okay, so our vector field on R3 is, say, F1, F2, F3. Each of those are scalar functions. So we said already that we're conservative. So that means it's the gradient of some potential function f. We don't know what f is yet, little f. But we know when we take the gradient, we get our vector field f1, f2, f3. And the gradient of little f is a vector field. The first component is the partial of little f with respect to x. The second is the partial with respect to y. The third is the partial with respect to z. So we don't know what little f is, but we know the partial with respect to x. Whoops. We know the partial with respect to y, and we know the partial with respect to z. So we know some information about f. We know the partial derivative with respect to x. So if we want to find f, we need to undo that partial derivative. Hang on, let me. Right, so if you take a partial derivative and you integrate it with respect to x, so you take the partial with respect to x, you want to undo that to get f, you integrate with respect to x. And remember, since we said the first component of our vector field f1 is the partial of little f with respect to x, we're just integrating the first component with respect to x. Okay, but here's the problem. So when you, so if we have, say, just a function of one variable, say just a function of x, right? Function of one variable. When we take the derivative, what stuff is lost? What gets killed off and becomes zero? Well, any constants. So when you differentiate, all constants become zero, they're killed off. And then when you integrate back that derivative, we don't know what happens with those constants. We're not sure. So there's a piece of that function that we're not sure about, whatever the constant was. And you can't recover that by integrating. So similarly, for functions of three variables, if we take the partial with respect to x of, say, a function of x, y, and z, we're treating everything but x as a constant. So anything just involving y and z is going to become zero. So terms involving only y and z become 0. And when you integrate with respect to x, we don't know what those terms were now. They're kind of lost. So when we integrate the first component with respect to x, we don't know any terms just involving y and z in our potential function. So let me say, our original function is, if you want to find anything involving x, you're going to get that by integrating with respect to x. But we're unsure of stuff that involves just y and z. There could be some terms involving just y and z, but you won't find them integrating with respect to x. But luckily, we can find those terms by integrating the second component with respect to y and the third component with respect to z. So let me just erase you. The second component we said is the partial with respect to y, so we integrate that with respect to y. When we do that, we're not going to find terms involving just x and z, because if it involves just x and z, it gets killed off when we take the derivative with respect to y. So integrating back is not going to find those. And then we take the integral of the third guy with respect to z. And similarly, that will not include anything involving just x and y. Oops. But putting all three together, we can get the original function back minus a constant, but constants are not important here, right? Anything involving x, when you integrate the first component with respect to x, that's going to show up. Anything involving y, when you integrate the second component with respect to y, that's going to show up. Anything involving z, when you integrate the third component with respect to z, that's going to show up. And putting it all together, that is everything. Oops. So what we do is we do these three integrals. And we're going to splice them together. And I'll say what I mean in a sec by that. To get a potential function, little f. So we're integrating the first component with respect to x, the second component with respect to y, the third with respect to z. And we're piecing these together to get our original function f. And so here's what I mean. You need to be careful because, well, let's do an example, and then this will show how this works. Yeah. Okay, so let's find a potential function for for the vector field on R2, 2xy, of course, plus y cubed, and then x squared plus 3xy squared, my goodness, so 3xy squared plus 2y. Okay, so first of all, I want to emphasize, you're only going to have a potential function if you're conservative. So if you were just given this and told to integrate it, first thing you would do is we would check, is this conservative, first of all? So we're telling you already it's conservative, but let's check it real quick. So let's check the cross partials. We take the second component and we integrate with respect to x. So x squared plus 3xy squared plus 2y. When we integrate with respect to x, we get 2x. Oops. Plus 3y squared. When we take the partial of the first component with respect to y, we get 2x plus 3y squared. So we've showed that it is indeed conservative. So it's going to have a potential function. So let's find that potential function. Okay. So for the last one, we had a vector field on R3. We integrate the first component with respect to x, second with respect to y, third with respect to z. Now we just have a vector field on R2, so we integrate the first with respect to x, the second with respect to y. And there's nothing involving z, so we don't do that. Two x plus 3y squared. I just took the partial of the second component with respect to x and the partial of the first component with respect to y. And both of those were 2x plus 3y squared. Yeah. Okay. So we integrate the first component with respect to x. So our first component is 2xy plus y cubed. So integrating with respect to x means it's the opposite of differentiating with respect to x. You treat everything but x as a constant and integrate as usual with respect to x. So 2xy, when you integrate with respect to x, becomes what? So y we're treating as a constant. 2x. Right. So 2x becomes x squared times y. It hangs around. So we get x squared y. And then y cubed, when you integrate with respect to x, it's just a constant. So it becomes x times y cubed. So now we found all the bits of our potential function involving x. But we don't know anything that just involves y. So to figure out that stuff, we're going to integrate the second component, oh my goodness, with respect to y. So when we do that, integrating the second component, x squared plus 3xy squared plus 2y. So integrating with respect to y, we're treating everything but y as a constant. Integrating as usual with respect to y. X squared becomes x squared y. 3xy squared becomes xy cubed. And 2y becomes y squared. And if there's anything just involving x, we're not going to see it in this integral, but we can get that from the first one. Okay, so here's what it means to splice these two together. The first integral, when we integrate the first component with respect to x, all of the terms that involve x in any way are going to show up here. And so that is the x squared y and the xy cubed. So we write these down. Those are terms in our potential function. However, any of those terms that also involve y are going to show up in the second integral, and you do not want to double count them, right? We've already accounted for those terms, and so you need to cross them out anywhere you see them later, right? If you add them again, then you're wrong because you're double counting terms that have already been accounted for. Right. So let me I want to emphasize this. When you integrate the first component with respect to x, you're revealing everything involving x in your potential function. Stuff involving x could also involve y. So those terms could also show up in the second guy when you integrate with respect to y. But they're referring to the same terms. So you don't want to add them together. Otherwise, you're double counting and you're going to get the wrong function. So you need to cross those out if you see them again. Okay. So the first guy gives us everything but stuff just involving y. And we get that from the second integral. Really, the only thing left is our y squared. So cross that out. And now we have a potential function. You could, of course, add a constant to this if you like, but we just need to find a potential function. So that's the process. You integrate the first component with respect to x, the second with respect to y, and if you're in R3, the third with respect to z. Write down all the terms in the first one, cross them out later down the list where you see them, and then go to the next integral, write anything that hasn't been crossed out, cross those out later, then go to the third integral, write anything that's left over. And that's how we get our potential function. Okay, any questions about that?
So it's only conservative if they're both equal to each other?
So it's if you want to see that a vector field is conservative, you do the check from the theorem.
And they have to,
so if you're on R2, you check that the partial of the second with respect to the first variable, x, is equal to the partial of the first with respect to the second variable, y. So the partial of f2 with respect to x equals the partial of f1 with respect to y. That's if you're on R2. If you're on R3, you check that the curl is the zero vector.
Okay.
Right. So we were on R2, so we did the cross partials check here. Okay, so quickly, let's do another. So let's find a potential function, an antiderivative, I like to think of it. For the vector field, f is (2xy) over z z plus x squared over z, and then y minus x squared y over z squared. Okay, so once again, I'm telling you this is conservative, but if you wanted to check.
3 minutes.
Okay.
3 minutes.
My class ends in 3 minutes, so.
Okay, cool beans.
Hey, is Aurelius coming?
Terrell,
No,
you're, there we go. Gotten better now. Okay. So we checked that we're conservative. In other words, check that the curl of our vector field is 0. And you can do that. We don't have time here, but that's fine. It's all good. It happens. It happens. But I'm telling you this one's conservative, but you could check that for yourself. Okay, so we want to find a potential function. So we integrate the first component with respect to x. We integrate the second component with respect to y. And the third component with respect to z, and we splice everything together. So 2xy over z. What do we get when we integrate with respect to x?
We should be getting x squared times y all over z.
Right, right. Careful. Easy mistake to make, Nick. You took the derivative there. We want to integrate with respect to x. So we get x squared y over z. And anything involving just y and z we're missing, but I won't bother writing that down. We'll pick that up when we do the other integrals. So z plus x squared over z, when we integrate with respect to y, z becomes yz, and x squared over z becomes x squared y over z. And y minus x squared z squared, y becomes yz. And when we integrate x squared minus x squared y over z squared, that's z to the negative 2. So when we integrate, that becomes negative z to the negative 1. So we get minus negative, so plus x squared y over z. We splice these together. So we start at the top. X squared y over z is a term. Everywhere we see that later, we cross it out because we've already counted it. Then we go to the next. Yz is a term. Everywhere we see that later, we cross it out. And then we go to the third and write down anything that's left over. Nothing left over. That's a potential function. And so is that plus any constant, but that's okay. It's just like finding an antiderivative, right? We don't care about the constant when you evaluate an integral.
Quick
Okay,
question.
and one last
about
thing I want to
these.
do, let's do an example of an integral really quickly. So you don't add, you can, if you like. So technically, like if you're talking about like an antiderivative, right? It's plus some unknown constant. So you could say plus some unknown constant if you like. So I guess don't get confused if that shows up on an exam. Like plus some unknown constant, like in a multiple choice or something, but you're not going to get points taken off for not writing the plus an unknown constant. And whoops, generally you're not going to be asked to find just a potential function. You'll be asked to evaluate an integral, in which case the constant doesn't matter because it's when you do at one point minus the other, the constants goes away anyways. So it doesn't matter. Okay. So let's really quickly do an integral. So let's evaluate the integral of the curve C of the vector field F. Where F is 2xy plus C x squared x. And C is going to be the curve, which is given by or parameterized by R of t is going to be 1 plus t, negative 1 plus 3t, 2 plus t. And t is going to go from 0 to 1. Okay, going to move really quickly here. Okay, so we're integrating a vector field, doing a line integral of a vector field. Remember I said, first thing we want to check is if f conservative, because if it is, then we could just use the fundamental theorem of line integrals, find a potential and evaluate at the endpoints and be done with it rather than evaluating a line or doing a line integral directly. So let's do the curl of f real quick. So remember the curl of f is del cross f. And so del is ddx, ddy, ddz. And f is going to be 2xy plus c, x squared x. So really quickly, so I times ddy times x, which is 0, minus ddz times x squared, which is 0, minus j times, okay, so that's ddz times 2xy plus z, that's 1, minus ddx times x, which is 1, that's also 0. And then we have k times ddx times x squared, which is 2x, minus ddy times 2xy, which is also 2x. We do indeed get the 0 vector. So we're conservative. So since we're conservative, we know all we need to do is find a potential function and evaluate at the endpoints. So let's find a potential function really, really quickly. So we integrate the first with respect to x. When we do that, we get x squared y plus xc. I'm just doing this without writing this down. Normally we would write this down, but I'm trying to go quickly. Integrate the second component with respect to y. That gets us x squared y. We've already accounted for that. And then the third with respect to z, that's xz. We've already accounted for that. So that's a potential function there. So C, we need to find the endpoints to evaluate it at. So C goes from So our starting point is going to be, so we're not told what the endpoints are, but we're told a parameterization. And so as we start at time 0 here, because t goes from 0 to 1. So when we plug in time 0, we're at the point 1, -1, 2. And we go to, the endpoint is at time 1. And when we plug in t equals 1, we get the point 2, 2, 3. Oh, hang on. Let me write that as a point, even though it's technically a vector, but whatever, that's fine. We're thinking of it as a point. So we have our endpoints. Let me just do this here. Okay, so our integral is just f at q, the endpoint 2, 2, 3, minus our potential at the starting point 1, -1, 2, and plugging those in, we see we get 14 minus 1, which is 13. And that's an example of an integral we could do using the fundamental theorem of line integrals. So check that you're conservative. If yes, find a potential function, evaluate at the endpoints. If no, you got to do the usual thing. Yeah. Okay. Any questions? Sorry, I went over here. My apologies.
Will you just send like the homework answers out in like a announcement? Is that how you're going to do that?
Yeah.
Okay. All right. Thank you.
All right. So I'm going over to the office hours and see you there. Or if not, I will see you on Wednesday and have a good rest of your day.